Mass spectrometer problem. In a mass spectrometer, a potential difference, delta V, is used to accelerate electrons. A 1.5 times 10 to the minus 3 Tesla magnetic field B exists between two charged plates and points out of the page. An electric field E also exists between the plates, but the charge of the plates and the direction of the electric field is not known. The electrons pass through the fields and then enter an area with only the same previous magnetic field. So the B here, magnetic field, is the same that's here. The electron beam is deflected in a circular arc with a radius of 3 millimeters. Show the charges on the plates and the direction of the electric field. Sketch the path of the electron as it is deflected through the last section of the mass spectrometer. That's piece over there. And what is the speed of the electrons as they exit the velocity selector? This right here is the velocity selector. What is the value of the charge to mass ratio, Q over M, of the electron as calculated from this problem? And we're down here at the questions, the final questions for this. What is the accelerating voltage in the tube? And how does the electron radius change if the accelerating voltage is doubled? Show the charges on the plates and the direction of the electric field between the plates. Sketch the path of the electron as it is deflected through the last section of the mass spectrometer. That's this area here. So we have our electron going like this, and we're going to use the right-hand rule. A positive charge will feel a magnetic force to the bottom of the page. You point your four fingers of the right hand to the right, the direction the charge is moving. Curl your fingers towards your palm, or just face your palm outwards, all right? Because that's where the magnetic field is. That's facing the magnetic field. Your thumb will point to the bottom of the page, but that's for a positive charge. Since the electron has a negative charge, the force is opposite. It is in the up direction, so that's what we draw. There's our magnetic force, has to be in the up direction. Well, it is. This must be balanced by an electric force to the bottom of the page, so the electron can go straight through. So here's our free body diagram. Since the electric force points to the bottom of the page, and the electron charge is negative, the electric field must point in the opposite direction to the top of the page. Electric fields point from positive to negative, so the bottom plate will be positively charged and the top plate is negatively charged. That's what we've shown here. The electron moves through this piece, the velocity selector, in a straight line. Then, when it just has the magnetic field acting on it, it still feels a force in the up direction. Initially, when it goes in, it starts curving, and the force is always going to be perpendicular to its motion. What kind of motion is that? That is uniform circular motion. So it's going to go like this in an arc. What is the speed of the electrons as they exit the velocity selector? That's this thing here. Well, we've got our free body diagram here, and we know it's not moving in the up or down direction, so the acceleration in the up or down direction will be 0. So the magnetic force minus the electric force has to equal 0. Put the electric force on the other side. Substitute in our values, our algebraic values, right? The magnetic force is QVB. The electric force is QE. Q's cancel. And V is equal to E over B. We put in our value for the electric field and the magnetic field. And when you use newtons per coulomb and Tesla, you come out with meters per second. So that's 800,000 meters per second. What is the value of the charge to mass ratio, Q over M, of the electron as calculated from this problem? So we're going to look at the third section here, where you just have the magnetic field. Sum of the forces is Ma. The only force acting, I think we said that earlier, is the magnetic force. And we're in uniform circular motion. So the magnetic force is equal to mv squared over r. What is the magnetic force? QVB. So QVB equals mv squared over r. What is the value of the charge to mass ratio of the electron? What's unique here is you're not just solving for one variable like we've been doing. We need to have two variables. So we don't want to solve for Q or M, but Q over M. So we need to divide the right-hand side by M. And whatever we do to that side, we have to do to the left side. So that'll give us Q over M, but then we have to get rid of that VB. So we'll divide the left-hand side by VB. We have to do the same thing to the right. And then let's see what happens to the left side. VB goes out, and we're left with Q over M. That's good. On the right side, M goes out. V cancels one of the V's here in the square, and we're left with V over BR. So this is good. We now substitute in our values, and that's the velocity we got on the previous slide, the magnetic field, and here's the radius of our semicircular orbit over here. And notice we said it was 3 millimeters, but we need to use meters. So you move the decimal over 3 places, you get 0.003 meters. And finally, our answer is 1.78 times 10 to the 11th coulombs per kilogram. Now you might question, how does meters per second and Tesla and meters all give us that answer? Well, as long as you use the SI units, and we've got a charge here over mass, the result will be coulombs over kilogram. What is the accelerating voltage in the tube? Use conservation of energy, as there is no external work being done on the electrons. So this term goes out, and the initial energy is the final energy. All the initial energy is the electric potential energy that the electrons have over here at the negative terminal. They get repelled, and they go that way through the field. At the end, there's no more accelerating voltage, and all they have are kinetic energy. So the equation for potential energy is Q delta V, and kinetic energy is 1/2 mv squared. Solve for delta V by dividing both sides by Q. What is the accelerating voltage delta V in the tube? So we have our equation here. Delta V is mv squared over 2Q. Let's rewrite that as m over q times v squared over 2. It uses the mass to charge ratio, mass to q, but we already have the charge to mass ratio. So we substitute m over q is equal to 1 over q over m, and we get this expression here, and then we can put our numbers in. We have the velocity, we have 2, and we have the charge to mass ratio. So we find that it's 1.80 volts. It's just a cooler way of doing it. How does the electron radius change if the accelerating voltage is doubled? Well, we have our equation here. We begin with this equation, okay, where we put in the charge to mass ratio. It doesn't have the radius, so we need to go back to part C for this equation here, where we had the radius of the electron's motion. And what do we see? If you increase the accelerating voltage, that will speed up the electron, which will then change the electron's radius. So we will rearrange this equation for V. So we have V is equal to Q BR over M. Substitute it into our accelerating voltage equation there. And then step on over here. And what do we notice? We have a Q in the M denominator. We'll factor and get rid of one of the Q over M's in the numerator. We get the accelerating voltage is Q over M times BR parentheses squared over 2, and then solve that for R. And we kind of left out some steps here, so please go through them, and hopefully you'll get this answer here. And we'll go to the next slide. So after all that algebraic manipulation, we wanted to come up with an equation where R is a function of the accelerating voltage. So if we double the accelerating voltage, right, that's within the square root sign, so the radius will increase by a factor of square root of 2.